Predicting erosion in any environment can be challenging, but is extremely difficult in forest environments due to the complexity of the landscape. Natural erosion rates in a forest environment are generally small, under 1/10 of a ton per acre, or 0.2 megagrams per hectare. Different activities, such as timber harvesting, can increase that erosion rate up to 1 ton per acre, or 2 megagrams per hectare. Prescribed fire, depending on its severity, can also change the erosion rates. And wildfires can increase it even another order of magnitude, all the way up to 100 tons per acre and 200 megagrams per hectare, depending upon the fire severity, soil type, topography, and precipitation patterns. To be able to use process-based models such as WEP, which is the Water Erosion Prediction Project, parameter identification is needed. We've been working on identifying those parameters during the past 10 years here at the Rocky Mountain Research Station. In forest environments, challenging aspects of erosion modeling include spatially varied and temporally varying soil properties, or varying amounts of ground cover for a given management scenario. For example, a prescribed fire that burns on a hill slope may not have the same severity at the bottom as the top of the hill slope. So therefore, these differences need to be identified and modeled to be able to accurately predict the amount of erosion that will come out at the base of the hill slope. In a forest environment, we've identified 4 different surface hydrologic units. They are an undisturbed forest environment, a low severity fire, a high severity fire, and a skid trail or highly disturbed units. In each of those different hydrologic units, modeling parameters also vary, and they must be accounted for to be able to accurately predict the amount of erosion that will occur at the base of a hill slope. This video will show you how we obtain some of the parameters that we use in the forest version of the WEP model. In the WEP model, to obtain 2 key parameters, saturated hydraulic conductivity and interval erodibility, a small 1 meter by 1 meter rainfall simulator is used. This simulator, a modified Purdue type, was built here at the Rocky Mountain Research Station in Moscow. It allows us to apply rain at varying rates to a plot on the ground 1 square meter in size. The rainfall rate can be varied. We generally use between 80 and 100 millimeters per hour. In the field, we go out and select plots under 4 surface cover treatments in forest environments. They are a natural or undisturbed forest environment, a low severity burn, a high severity burn, and a skid trail or other major disturbance. To establish the plots, uniform slopes are picked out within each of those treatment categories. Metal borders are placed in the ground with a collection trough at the base of the plot. The collection trough has to be placed such that there's no leakage. Bentonite and silicon sealer is used to seal the metal border to collect all the runoff at the outlet of the trough. Prior to raining, ground cover measurements are made by using a grid frame over the plot area and determining what the surface cover is and the type. A calibration pan is installed over the plot to calibrate the rainfall simulator to determine the exact rainfall rate being applied. Once the simulator is started, time bottle samples are used to collect the runoff and sediment at the base of the plots. Typical run lengths are 30 minutes to 1 hour. On some experiments, we run the simulator under 3 moisture regimes. The existing moisture content on one day, the following day a wet run which is in a saturated condition, and finally a third run which is in a very saturated condition. Runoff samples that are collected are then processed in the laboratory back in Moscow to determine the infiltration rate and the erodibility. Runoff hydrographs are generated from this information. Various plot sizes have been used to collect the information we need for the WEP model. We've used plots 1 meter by 5 meters in length, and also plots 3 meters by 7 meters. Using these larger plots forced us to use a larger simulator, the type that is commonly referred to as a modified Purdue type simulator. This was difficult and challenging work to carry these simulators down steep forest terrain to be able to get the parameters that we needed for the WEP model. Some of our erosion work has involved prescribed fire. To determine the severity of the fire, we take several pre-fire measurements. We measure the thickness of the duff, we measure the moisture content of the duff, we've measured the different fuels that are going to be burned in different size categories, we measure the moisture contents of the fuels. All this information will help us characterize the fire, which we then can relate to the amount of erosion that had occurred after the fire. Ignition of prescribed fires is done in several ways. Hand drip torches can be used, or aerial ignition with a helicopter. We've done several prescribed fires over the last 10 years under a variety of weather and moisture conditions to be able to look at how different severity affects erosion. After the fire, burn sites generally have very little duff remaining if the fire was of high severity. If the fire was low severity, there's often duff remaining protecting the mineral soil from erosion. Our research has been working heavily in determining the impact of prescribed fire on the erosion process. To determine another key parameter for the WEP model, real erodibility, concentrated flow is used in a forest environment down natural flow paths. For this experiment, we pick out our 4 surface condition, a natural undisturbed area, a low severity burn area, high severity burn, and skid trail or other major disturbance. Concentrated water is applied at varying rates over a 4-meter length, simulating a rill that would form from a larger contributing area. The flow rates that we use are 7 liters per minute, 15, 22, 30, and 48 liters per minute. We run this experiment on 3 different slope classes, a 20%, a 45%, and a 65% slope. By applying water, we're able to generate a rill that is either in a single flow path or in multiple flow paths down the hill slope. At the base of the hill slope, a bottle is used to collect the runoff to determine the amount of water and the amount of sediment that comes off. Green dye is introduced to the water to help us determine velocities. A salt concentration is also used for that purpose with conductivity probes. Within a given flow rate, the erosion rates decline, indicating a detachment limiting situation. Armoring does occur. The information gained from this experiment is used to determine rill erodibility, and we can use that to compare the shear model and the stream power model on the unit sediment load. A lot of variability is common in forest environments for each of these surface conditions. This variability must be included in any effort to model these conditions. To validate the modeling efforts, subcatchments are instrumentated to determine the amount of runoff and sediment that will leave a large hill slope. Common conditions that we install these watersheds on are prescribed fires, wildfires, and mitigation treatments. These watersheds provide a mechanism to determine the exact amount of runoff and sediment to leave large hill slopes. To do this, we install a sheet metal cutoff wall, a flume system, and a sediment trap. This system allows us to determine the runoff and sediment that would leave that site for any given storm. Sediment traps and flumes are located just beneath the outlet of a culvert where the water is directed into the flume and then to a sediment tank. A weather station is installed on site to determine meteorological parameters. Some of this information is transmitted via cell phones back to our station in Moscow. One of the most important weather parameters is rainfall intensity. Tipping bucket rain gauges are used for that, and generally we will have several rain gauges for a given subcatchment basin. After each rainfall event, the sediment that is collected in the storage box is cleaned out. Generally we use 5-gallon buckets and a hanging scale to determine the amount of sediment that was trapped for that given storm. Subsamples of the sediment are collected for moisture content and particle size analysis, which are processed back in Moscow. After wildfires, various mitigation treatments are often used to help reduce the threat of runoff and sedimentation. One treatment is contour fell logs, where trees are felled and placed on the contour and filled in on the bottom to act as a sediment trap and to reduce any runoff that would occur on that hill slope. After each storm, we measure the amount of sediment that is trapped by each log. All of these efforts are to improve our understanding and prediction of soil erosion in forest environments.